In Chapter 16, we combine the concepts we learned in Chapter 14 about equilibria with the ideas we had learned and just reviewed about acids. And we start talking about acid-base equilibria in aqueous solutions. Now, if you look at this, you'll see there's quite a bit of homework in the book. And the important thing to note is that Chapter 16 is huge. So the second test covers 14 and 15, which are small, and part of 16. And Exam 2 stops on page 1625. And you don't need to flip there and mark it because it's already marked in your notes. Exam 2 stops here. So the first thing that we need to understand about aqueous solutions is that aqueous solutions are made of water. And it is the water in there that helps us to have some acid-base behavior going on. And we need to understand what water is doing when it's just sitting in a beaker by itself. Water is H2O, and it can auto-ionize to make a hydrogen ion and a hydroxide ion. Now, I typically write the ionization of water as H2O is in equilibrium with H plus OH minus. We've already introduced this idea of the hydronium ion, that the better representation of a hydrogen ion or a proton in water is the hydronium ion. So we can also write it as two waters reacts to make the hydronium plus the hydroxide. And this means the same thing. Now, we can set this up and write an equilibrium expression because it is an equilibrium dissociation. So we introduce this saying our K. Now I'm not going to call this a Kc or a Kp. This has a new name and we call it Kw for water. So Kw is equal to the hydronium ion concentration times the hydroxide concentration. And you remember, we don't divide that by the concentration of water because water is a liquid. And we don't put liquids in our equilibrium expressions. You'll also see me write it most of the time as Kw is equal to H plus times OH minus. The reason a lot of the textbooks put that second molecule of water in there is because when they do that, it tells you that water's in there. So when we get to basic behavior and you need water to produce hydroxide, you're accustomed to having the water in the equation. Now, the ionization of water is quite small, so the water concentration is held constant. So again, that's why we don't put it in there. Now, this Kw is something that's been studied a lot. It is the ion product constant of water. And Kw, like all equilibrium constants, varies with temperature. So we have to deal with this idea that we have a different value for Kw with a different temperature. For our purposes in this class, unless we specifically say otherwise, we'll be working at 25 degrees Celsius. So we work at 25 degrees unless otherwise stated. So as you do this over and over, you will learn that Kw for us is equal to 1 times 10 to the negative 14th. Now, in this chart, we only have 2 sig figs, but there will be times it's okay to use 3 sig figs. Kw is 1.00 times 10 to the negative 14th when it's appropriate to use 3 sig figs. Now, the concentrations of the hydrogen and a hydroxide ion are always related to Kw with this relationship regardless of what the numerical value of Kw is. So at 25 degrees, hydrogen times hydroxide is 1 times 10 to the negative 14th. But at 60 degrees, hydrogen times hydroxide is still Kw, but now it's 9.5 times 10 to the negative 14th because you're at a different temperature. And this relationship between them tells us whether or not something is acidic or basic. We tend to come up to this point in time thinking that if we have an acid, we have hydrogen ions in solution. And if we have a base, we have hydroxide ions in solution. The truth is you have both of them in there all the time. And it's really not the fact that you have hydrogen or hydroxide, it's the relative amounts of the two that makes something acidic or basic. Because you always have water doing its autoionization, giving hydrogen and hydroxide. So even if you dump in a strong base or a weak base from another source, you'll get more hydroxide. Or if you dump in an acid, you get more hydrogen ion. But you still have some of the other. So we decide if something is acidic or basic looking at the relative amounts of the two. In an acidic solution, the proton concentration is bigger than the hydroxide. In a basic solution, the proton is less than hydroxide, and in neutral, they're equal. So let's look at a typical problem that you might encounter. The hydrogen ion concentration is 4.6 times 10 to the negative 8th molar in blood at 25 degrees C. Calculate the hydroxide concentration and decide whether or not it's acidic or basic. Well, we know that the hydrogen concentration times the hydroxide concentration is equal to Kw. I know the hydrogen ion concentration here, so the hydroxide concentration is equal to Kw divided by the hydrogen concentration, and that's equal to 1.0 times 10 to the negative 14th, because I'm at 25 degrees, divided by 4.6 times 10 to the negative 8th molar. And so I get the hydroxide concentration is 2.2 times 10 to the negative 7th molar. So now I look at the two numbers, the hydrogen concentration and the hydroxide concentration, and I compare them. My hydrogen concentration is 4.6 times 10 to the negative 8th molar. My hydroxide concentration is 2.2 times 10 to the negative 7th molar, which is bigger. The hydroxide is bigger, so the solution is basic. Okay, go ahead and try the one on the next page at your seats.